This lecture looks at games of chance, like lotteries, dice, even tossing coins. Can mathematics help us win? We'll see how a Frenchman's gambling problem instigated the whole field of probability. We'll find out why you should never buy a British lottery ticket on a Monday. And we'll learn how Voltaire got rich on a lottery using a simple bit of mathematics. But let's start with one of the oldest games of chance, and that's dice. So dice have many advantages. They're inexpensive, cheap to make, easy to carry. You can put them in your pocket, you can take them with you wherever you go. And people have been playing games with dice for a long, long time. I want to tell you about a game that was quite popular in France a few centuries ago. And I'll just say the dice I'm going to be talking about today are always the standard dice. So each die is a cube. It's got the numbers 1 to 6 on its faces. And we'll assume that they are fair, they're unbiased. The chance of throwing any one of the numbers is 1/6. Okay, so your mate, Antoine, comes up to you and says, I bet you 5 francs that I can throw a 6 if you give me 4 goes. Should you take that bet? What do we think? So let me tell you a little bit more about Antoine. Full name, Antoine Gambeau, Chevalier de Marais. Nobleman. Well, sort of. He actually gave himself that nickname. But everyone started to call him that anyway. And he was very interested in gambling and in calculating mathematical odds. He got a bit stuck on some of his calculations, and one of them was related to this game or a version of it. So let's see what we can find out about this game. So you've got 4 goes to throw a 6, and that means there are actually 5 possible ways the game can turn out. Here they are. So you throw a 6 straight away, possibly, or you fail, but then you manage on your 2nd attempt, or your 3rd attempt, or your 4th attempt. And the only way to lose in this game is to fail consecutively 4 times. So, of course, we're not going to say, well, that means you have an 80% chance of winning, because 4 of the 5 outcomes lead to you winning. We won't say that, and the reason we don't say that is because we have no reason to think that these outcomes are all equally likely. So we need to understand what are the probabilities of each of these possible outcomes. Okay, well, the first one, maybe you just throw a 6, you're lucky, straight away you throw a 6. The chance of that happening is 1 in 6. There are 6 numbers on the die, and 6 is one of them. So there's a 1 in 6 chance of that happening. Fine. What about the next one? Well, in that outcome, we failed on our first attempt, and then we are lucky and we do throw a 6. Now, the probability of throwing a 6 is 1 in 6. So the probability of throwing a not 6, one of the other 5 numbers, will be 5/6. So I claim that the chance of throwing non-6 followed by 6 will be 5/6 times 1/6, which is 5 out of 36. Now, why am I saying that? Well, it's an example of a general rule of probability that says if you are looking at independent events, ones which do not affect each other, the outcome of one does not affect the outcome of the next, then there's a rule that says this, that if the probability of event A is P, say, and the probability of event B is Q, say, then if they are independent of each other, they don't affect each other, like consecutive rolls of a dice, then the probability of both of those things happening, you just multiply together P times Q. Now, I must stress they have to be independent events. They cannot be events that influence each other in any way. For example, here is a false conclusion, one that you should not apply this rule. If we know, say, that about 1/10 of adults have a beard, and we know that about 1/2 of adults are women, we cannot multiply those together and conclude that 1 adult in 20 is a woman with a beard. Not true. However glorious that would look. So, however, luckily for us, throws of a die are independent of each other. So the outcome of one roll does not affect the outcome of the next. So we really can multiply those probabilities together and get, as we've seen, 5 out of 36, a probability of 5 in 36 of the second outcome there. And you can repeat that idea and work out the chance of having non-6 followed by non-6 followed by 6. and non-6, and then finally a 6 on your 4th attempt. And you can get all of these written down. There they are. Those are all those probabilities. You can do the calculations. So what's the chance of winning in this game, of eventually managing to get a 6 if you have 4 goes at it? Well, we can just add up all of those 4 things. And if you do that, as I'm sure you have all just done in your head, you get 671 out of 1,296, which is about a 52% chance of winning at this game. So we should not take our friend Antoine's bet when he sidles up to us, because over the long term, he will have a better chance of throwing that 6 than not. Now, there's actually a better way to do this calculation. We worked out those 4 things step by step and added them all up, but instead, we could just say, well, our chance of winning is 1 minus our chance of losing. So if we have we can work out the chance of losing. The only way to lose is to fail 4 consecutive times to throw a 6. So that's a 5/6 chance multiplied by itself 4 times. We're trying it 4 times. Okay, so we get this calculation here, 5/6 to the power 4, 625 over 1296. That is the chance of losing. It's the only way we can lose. So if that's the chance of losing, then the chance of winning is 1 minus that. And we get that same outcome at the end. So that's a slightly quicker way if we notice to do that. And that's going to be useful to us later. So after a while, Antoine finds that he's sort of getting a bit bored of this game, or maybe no one wants to play it anymore with him because he somehow keeps winning. So he's experimenting with variants of it. And one he comes up with is this. Okay, we've been trying to throw a single die and throw a 6, and we're having 4 attempts at it. How about I make it a little bit more spicy, and instead I throw a pair of dice, 2 dice, and I try to get a double 6. Now the chances of getting a double 6, well, both of the dice have to be the 6. There's a 1/6 chance for each of them, so 1/6 times 1/6, 1 in 36. So you've got a 1 in 36 chance on any given try to throw a double 6. So Gombo said, right, 1 in 36, that's 1/6 as likely as throwing a 6 with a single die. So there's this old gambling rule that says that what I can do is I can say, well, this alternative is 1/6 as likely as throwing a 6 with a single die. I know that has a 52% success rate with 4 attempts. So with this thing that's 1/6 as likely, what I should do is have not 4 attempts, but 4 times 6, so you sort of make up for the less likeliness. You should have 24 attempts, and that will give you the same 52% likelihood of success. This is Gombo's idea, and so he thinks this is what it should be, but unfortunately, it doesn't seem to be working out that way. So he had a friend, and he asked his friend for advice. And luckily for Gombo, his friend was one of the best mathematicians in France, Blaise Pascal. And Pascal, he had a friend as well. And he asked his friend about this question and a couple of others, and his friend was one of the other best mathematicians in France, Pierre de Fermat. Right, there they are, Pascal on the left. He's looking at cycloids in that statue. It's a good statue. And Fermat is on the right. So they have a series of letters that go between them. And in that series of letters, they pretty much establish the field of probability and mathematical study of probability. They get a lot of the basics right and established and worked through. So we can solve this question. Was Gombo right? Was this intuition right? And if not, what's the right answer? So we're interested in throwing a double 6, and we're going to have 24 goes at it. And Gombo said this should give you a 52% success rate, so it should be a good bet in the long run. Now, we don't want to add up 24 different potential outcomes. We'd be crying by the time we did that. So let's instead say, how could we lose? And the only way we can lose is by failing 24 consecutive times to throw a double 6. Now, the chance of throwing a double 6 in any one attempt is, we've seen, 1 in 36. So the chance of failing to do that will be 35/36. Okay, so if we're going to fail 24 consecutive times, then the chance of that will be 35/36 raised to the power 24. And then that's the probability of failure, so the probability of success is 1 minus that. Brilliant, so we just put that in our calculator and work it out. Only, Pascal and Fermat do not have our calculator, or any calculator, right? So what are they going to do? Well, how can they work? Would be, I don't want to be doing that by hand. Nobody wants to do that by hand. Luckily, there is a mathematical result that can help us do precisely this kind of calculation. It's really, really useful. And it's called the binomial theorem. And if you've heard or used the binomial theorem, you'll be thinking, hang on a minute, that's got something to do with multiplying out brackets, and indeed it does. It tells us how to work out expressions like a plus b all to the power n, right? So by for two things, that you've got two terms in your bracket. So you want to multiply out a bracket by itself n times, a great big algebraic calculation. And the theorem tells you how to do that, what the coefficients are of all those terms. Now, a special example of this, which is relevant to us, is something like this. If you wanted to work out 1 minus x to the power 24, then the theorem will tell you it's an expression that looks a bit like that. Some x's, x squared, x cubed, and so on, higher powers of x. And those coefficients that I haven't explicitly stated, what I've called u, v, and w, the theorem tells you exactly how to find those. We call them binomial coefficients. Now, the useful thing for us here is that if your x in that expression, if x is a small number, then x is already small, x squared is very small, x cubed is tiny, and every higher power of x is increasing, well, it's very, very, very small. And after a while, it's kind of negligible. If you just want an approximate answer, you can ignore those higher terms in x because they're very, very small. So, what's our x going to be? Well, if we want to work out 35/36 to the power 24, that's 1 minus 1 over 36. So our x is 1 over 36, which is small. And so we can just calculate the first few terms of this long expression. We don't care about the higher powers. We just have 2 or 3 terms, and it will give us a good enough approximation. And the approximation we get is about 0.51. So that's a 51% chance of failing to throw a double six. The odds are kind of switched over. Gombo is more likely, so his chance of succeeding to throw a double six in 24 attempts is less than half. It's a 49% chance. So actually, we should take that bet if he asks us to do this, because he has a 49% chance only of winning, and we would have a 51% chance, therefore, of getting money from him. So it's wrong that that little intuition there, the old gambler's rule, didn't work out, and we can prove why. But we have to use something like the binomial theorem to do so. I will just mention another of the problems that Pascal and Fermat discussed in their letters, because it does have applications today, in people are thinking about how to bet on sporting events or something like that. It's known as the problem of points. And the idea is that you've started playing some game, you're gambling on something, dice or coins or something, rain stops play. So I keep the Duckworth-Lewis method. It isn't quite that. It's not going to be as bad as that. Something stops the game, or you're at a point in the game, and you want to know, actually, how have the odds changed based on what's happened so far? So you might go into, say, you and I are tossing a coin, and it's the first to 3. So maybe I've chosen heads, you've chosen tails, and we've thrown heads, heads, tails. So I just need 1 more head. You need 2 more tails. So I've clearly got an advantage at this point. Clearly going to have a more than 50-50 chance of winning now. But exactly what chance? How should we, if the game is abandoned at this point, how do we divvy up, how do we share the kitty or the pot if we have to stop at this point? So you could reason it like this. You could say, there's only 3 ways this game can end now. Right, if the next throw is heads, we're done, I've won, because I've got 3 heads. Or the next throw could be tails, but then if after that it's heads, I've won again, because I still have my 3 heads before you've got your 3 tails. And so the only way of those 3 possible end games where you would win is if it's 2 tails consecutively. So, therefore, I should get 2/3 of the kitty. Well, no. No, again, the issue is these things are not all equally likely. And what Pascal and Fermat sort of realised was that you've got to consider all the potential things that could happen, even if they don't actually happen during gameplay. And the reason you do that is so that you can consider all the events with equal likelihood. So if you toss a coin 2 times, there are actually 4 possible outcomes. Heads then heads, heads then tails, tails then heads, or tails then tails, right? 4 equally likely outcomes. So you can put those in. Now, the first 2 of those, you never actually play to the conclusion of those, because as soon as you've thrown that next head there, the game is over. But you still have to include those sort of shadow, ghost, potential universes in your calculation, even though no game could list that sequence of throws, because you would stop before you get to the end. When you do that, when you list even the sort of potential outcomes, even if they may not happen in gameplay, it's then very easy to see, okay, there are 4 of these, all equally likely. In 3 of them, I win. I've rigged this, clearly. In 3 of them, I win, so I should get 3/4 of the kitty if we have to stop at this point. Okay, so that's the kind of deduction that they were making. Now, this kind of reasoning was really one of the very early attempts to properly lay down some foundations of the theory of probability, and it went from strength to strength. But I want to give you a couple of examples of a general principle, really, that human beings, as a species, we are poor at probabilistic intuition. We don't seem to have very good intuition when it comes to risk and chance and these kind of things. And I just wanted, I'm not saying this, to crush our self-esteem, but knowledge is power, and so if we know this about ourselves, we know we're not great at interpreting statistics, then it just means we can be a bit more vigilant, right? So to make us feel better about our own, imperfection as humans, I want to give you just 2 examples of really pretty good mathematicians who made what we might call basic errors of probability. And this is not me saying that they're bad mathematicians. They are great mathematicians, and so it's even more surprising you could say that they would make some errors. So here are 2 questions, right, that I'm going to give you some surprisingly incorrect answers to. The first one, if a coin is tossed twice, we just talked about this actually, what's the probability of getting at least 1 head? And the second question, throwing 2 dice, which total is more likely to get, 11 or 12? Okay, so first one on the left, let us hear the answer of extremely good mathematician Jean-Laurent d'Alembert, who wrote an encyclopedia article about it. This is after the time of Fermat and Pascal. But here he is. He says the possibilities, if you're trying to get at least 1 head, well, you could throw a head straight away, or you carry on trying, and it could be tails, but then heads, or it could be 2 tails. So 3 possibilities, 2/3 of the time you get a head, so the probability is 2/3. Right? It's that same incorrect thing that we talked about a moment ago. The real answer, no, is 3/4. And it's again because he didn't consider outcomes that you would never play to their completion, because you already stop when you get ahead. So this guy is a really amazing mathematician. If you ever have done or will do a maths degree, you will hear about some of his mathematics. But he made this silly mistake, even he. And here's another amazingly, Leibniz. What a guy, right? Invented calculus with Newton. He has a biscuit named after him. That is how amazing he is as a mathematician. We can only dream of such fame. So Choco Leibniz here says it's equally likely to throw 12 pointers 11 because, what does he say? One or other can be done in only one manner. So what he means here is, to throw a total of 12 with 2 dice, they both have to be 6. To throw an 11, you've got to have 1 5 and 1 6. There's only one way to do it. But that's not, that's not quite right. Temporarily, you have to care that you have 2 different dice, and you have to care which one is which. Because you could have the one on the left could be 5 and the one on the right could be 6. Or the one on the left could be 6 and the one on the right could be 5. Right? Oh, I said that right. Anyway, so you could have 5 and 6 or 6 and 5, and those are actually different temporarily from your point of view, right? So there are actually 2 ways to throw an 11. It's twice as likely to get a total of 11 as it is to get 12. And, even the great Leibniz could make a little mistake like that. So just, watch out. The biggest mistake that it's very tempting to do, it's a beguiling error, is to say something like, I've thrown 4 heads in a row, so I'm overdue to get a tails, and you sort of feel like the universe owes you the other outcome because you know that they're equally likely in the long run, but of course coins don't have a memory, roulette tables do not have a memory. This is the gambler's fallacy of saying, you know, we know what the odds are in the long run, and therefore you start to think, oh, well, I'm definitely going to get it this time it's got to happen. So on a roulette table, you might bet on red and black. Those are equally likely to occur. Just the odds are slightly less than 50% because there's actually a sneaky green one in there as well. That's how the casinos make their money. This is a beguiling fallacy. It isn't true. You know, the roulette table, the dice, the coins, they don't remember what's happened. They don't have a sense of, you know, moral justice. It's randomness. And the point is, if you're talking about tossing coins, any sequence of heads and tails that you specify exactly is equally likely as any other. If you have a sequence of 6 coin tosses, there's a 50-50 chance at each stage of heads or tails. So you multiply those halves together, 6 of them, you get a 1 in 64 chance of any particular specified sequence. So it's a 1 in 64 chance of getting 6 heads in a row. But there's also a 1 in 64 chance of getting 5 heads, then a tail. And you don't know which universe you're in when you've had 5 heads. You don't know if you're in the universe of 5 heads, then another head, or 5 heads and a tail. At that point, they are equally likely. And so you cannot do this kind of, oh, I'm overdue a head, or a black or a white. However, here is my top guaranteed strategy to always win at roulette. Right, you ready? This is amazing. Free to you, because I love you so much. Right, what you do is, you put, your initial bet is, say, $1. Right? I don't know why I decided dollars felt more gambly. Anyway, initial bet is $1. And so when you're doing this, when you're betting on red or black in roulette, if you bet $1 and you're correct, then you would get $2 back, so you sort of double your money. You get your bet back and the same amount. Right, so my strategy is, you keep going. Every time you lose, you double your stakes and bet again. So let's do a little example. Suppose you're betting that black will come up, and it doesn't come up until the 7th go. So at that point, let's see, what are we betting by the 7th go? So we've got $1, 2, then 4, then 8, then 16, then 32, 64. So we've bet $64 then on the time we finally do win. So our winnings will be $128, double that. How much have we actually spent? Well, it's all that 1, 2, 4, 8, 16, 32, and 64. That's our outlay. And it's a fact about these kind of progressions. If you add up all the powers of 2 to a certain number, to a certain point, then the sum of all of those is the next power, take away 1. So the sum of all of those up to 64 will be the next power, 128, minus 1, 127. So we actually, our profit, we have made a profit, but it's always just $1. It's the same as our initial bet. Now, you can address this. You say, fine, my initial bet will be $1 million. Right, so then I'm going to definitely make $1 million profit. That's great, except, well, you have to have $1 million, but you have to have more than $1 million, right? Because you could go, and this is not by any means unusual enough to not worry about, that you would have to go 6 or 7 steps or even more. And by the time you get to that point, how much money have we laid out? If we put $1 million initially, well, $127 million investment to only get $1 million back. And at any point, you could run out of money. The casino could say, you've reached the maximum bet you can place, or they can just say, we don't like the look of you, go away. So this is perhaps quite a risky strategy, but it does work in theory. And I'm sure they wouldn't mind if you did it with $1. They may not be too happy if you're betting 64 million. If you've got $64 million, you don't need to be wasting your time. just have a lovely time. Don't worry about gambling. So you do sometimes hear of mathematicians or mathematically minded people winning money at casinos. It's almost always by playing this game, Blackjack. Now in Blackjack, what happens is you're playing against the dealer, you each get 2 cards, And then you can decide whether to take more cards at any point or to stick with what you've got. And the goal is you want to get to a total of as near as you can to 21, but not go over, not go bust. So at any point, so here you have a total of 16, right? So you have to think, okay, do I want to take another card and try and get closer to 21? But then the risk is, maybe I take this and it's a 9 and then I've gone bust. And the dealer is doing the same thing. If they go bust, then you win by default, however far away you are. But the dealer has to obey the following rule, that if they are on 16 or less, they have to take another card. So it is in your interests for the play to have reached a point where lots of small cards have already been played. And so if that happens, and this is what the card counters are doing, they're monitoring the number of small cards that are still left in play. If there are very few, then the chance that the dealer will go bust gets higher. So they can sort of gauge how good the odds are and change their bets accordingly. This method, yes, it can work. At its best, if you're doing it absolutely perfectly, you get at best a 1% advantage over the house, the casino. Any mistake, and you risk losing all that. Also, you can't be winning too ostentatiously because they're not compelled to have you as a customer. So although people have been able to win money at this, it's getting harder. One way it's getting harder is that the casinos are adding more decks of cards into the mix. So, a long time ago, you might just have one deck of cards and then you'd play and play until they were all gone, and then you'd start again from the beginning of the deck. So it was sort of easier for changes to make more of a difference. Now they can use up to 8 decks of cards at once. So that, the variance in that becomes big enough, it's harder to make this pay. But this precisely is working because it's not random. So what I'm really talking about today is randomness, lotteries, dice and things. This is only possible because there isn't randomness. It's not independent what comes next because you've been looking at the cards that have already been dealt. So I'm not going to talk any more about it here, but that is precisely possible because of non-randomness. Okay, but I've promised you lotteries, so let's talk about lotteries. The earliest lottery, I think, in England was a state lottery that Elizabeth I decreed there'd be a lottery. It was to raise money for the Navy. Tickets were 10 shillings each. That is a lot of money in Elizabethan times. So this is not for everyone. You have to be pretty well-to-do even to buy a ticket. The prize was astronomical, £5,000, but not all in ready cash. You got some tapestry, you got some plate and some linen, fine linen, well, it better be fine linen cloth in the mix. So it's kind of an interesting prize, cobbled together everything they could find. Here you go, this is what you'll get. So this was supposed to raise money. I don't think it actually quite succeeded, but that's the first lottery that I'm aware of in England. It was more what we'd now call a raffle, actually. Modern lotteries, we'll do a sort of little toy example, but modern lotteries all tend to have the form of you choose some numbers from a wider selection of numbers. So in the UK, you choose 6 numbers that are between 1 and 59. It used to be 49, then it went up to 59. And then if you match all 6 numbers, that's how you win the jackpot. So we'll work up to that, but we'll do a little toy lottery first. Now toy lottery, we're choosing from numbers between 1 and 10, and we choose 2 numbers, and to win the jackpot, we have to match 2 numbers with what comes out in the exciting draw. So, what are our odds of winning this toy lottery? Think about this. How many ways are there of choosing 2 numbers from a set of 10? That's what we need to know, because that's the number of possible lottery tickets. And there's one winning combination, so out of all the possibilities, we've got a 1 chance out of all that. So how many possible ways are there of picking a set of 2 numbers out of 10? Well, you imagine them all there in front of us. We pick our first number, there's 10 ways to do that, because there's 10 numbers in front of us. Then we pick our second number. Now there's only 9 ways to do that, because we've already used up one of the numbers. So the total number of ways to do this is 10 times 9, 90. However, that forgets that we're actually going to see each combination twice. Because if, say, you had a 1 and a 5, and that's your winning numbers, well, you could have drawn a 1 first, then a 5, or you could have drawn the 5 first, then the 1. Either one of those will result in the same set, 1 and 5. So every actual pair is is going to appear twice in this selection process of 90 kind of ordered pairs, sequences of 2 numbers. So we've got to divide that 90 by 2, and we get, really, there are 45 pairs. So it's sort of AB equals BA in this situation. So our chance of winning, then, if we want to pick the 1 that is the jackpot winner, that's a 1 in 45 chance. Okay, step 2. Let's imagine that's too easy to win. Let's now say, okay, for the jackpot, you actually need to match 3 numbers. So now, what are we going to do? How many ways are there of picking a set of 3 numbers out of 10? Well, you do the same thing. You pick the first number, there's 10 ways. Then the second number, there's 9 ways to do that, 9 numbers left. And then the third number, there are now 8 numbers left. So that's how many choices we've got there. So we get 10 times 9 times 8, which is 720 of these sequences, right, of numbers, A, B, then C. But you're again going to get copies, because it doesn't matter. You don't care the order that you drew the numbers out in. You just care what the numbers themselves are. So it turns out, and I've written down the possibilities here, there are 6 ways of rearranging a collection of 3 things. So you can have the number A could be first, you could draw that out first, or you could draw B out first, or C out first. So there's 3 possibilities for the first number you drew out, because you've got a collection of 3 that you have to get. So there's 3 ways to get to have the first number, and then 2 ways to get the next number, because there are 2 numbers left in your special selection, and then the final number, you've got no choice. It must be that third one in the set that you're interested in. So 3 times 2 times 1, ways to do it, which is 6. And you may notice, I know I get very excitable, but that exclamation mark is not just me going, yay, 3. That symbol is pronounced in mathematics factorial. And that means 3 with a little exclamation mark, that means the product of all the numbers up to 3. And in general, n factorial means multiply all the numbers from 1 up to n, all the whole numbers. So 4 factorial, for instance, would be 1 times 2 times 3 times 4, 24. That would be the number of ways of arranging 4 numbers or objects, because you could have any of the 4 in the first place, then any of the 3 remaining in the next place, then 2, and then 1. Okay, so we have 720 sequences of 3 numbers that we've drawn out, but every collection, every set of 3 arises in 6 ways. Those are the 6 ways. So we've got to divide that 720 by 6, which I believe is 120. So this lottery, you have a 1 chance in 120 of happening upon the correct set. All right, so the final little one now, we know how to do this. What about choosing 4 numbers from 10? So a bit of notation. We call that 10 choose 4, that number. And there are different ways of writing it, but my favourite way is you put a 10 and then a 4 and then brackets round. So I've done that there. So we know how to do this. Oh, here. I've got the last little number missing. Looks all right on my screen. That should be 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1. So we've picked our 4 numbers, but then each set occurs in 4 factorial, 4 times 2 times 3 times 2 times 1, 24 ways. Now, there's a sort of sneaky little trick you can do to write this in a more efficient way with lots of factorials in. So I'll just show you that. A little bit missing on the end. It'll all be there in the end. So what I've done, this looks worse, but I promise you it's better. I wish I had the product of all the numbers from 1 to 10 on the top. And so I've made that happen. I've forced that to occur by just finishing that list, 6, 5, 4, 3, 2, 1. But then I've put it on the bottom of the fraction as well, so we haven't broken the law. These things are equal. And now if you do that, you find that what you've actually got is 10 factorial on the top, and then 4 factorial and 6 factorial on the bottom. So it's a kind of a neat, nifty way of writing it. And you can work it out, it's 210. Now, this is a cute little expression, and it works in general. So we've done 10 choose 4, but the same bit of reasoning works to tell you that the number of ways of choosing R, a set of size R, from a set of size n, so R numbers out of n, is this same sort of expression with factorials in. But I have to accept that's quite a lot of calculating and multiplying and dividing. So I want to show you another context that these numbers arise in, because it gives you an alternative way of finding these numbers that has a lot less multiplying and dividing. Okay, so imagine you're in one of those cities that we don't tend to have in Britain that actually is kind of well organised and is laid out on a grid system, a bit like in the middle of New York or something. And if you're trying to get from place to place, if I've got a point O and a point P, then I'm trying to get from O to P, you're trying to work out a route. Well, there might be lots of valid routes, but everything you do is either going right or going up. So you're moving through the grid. No weird higgledy-piggledy curvy lines. So you're only interested in shortest routes, so you're not going to go down or left or do anything weird like that. So to get from O to P, you really, I'll just give one example there. Every route will involve going at some point right 2 steps or blocks, and at some point up 3. So the total kind of distance you've travelled is 5, 2 right and 3 up. But you can do it in any order you like. So there's one route there that's right, up, right, up. But there are many others. The question is how many? Well, that's not too difficult to answer because any route can be specified exactly by saying where in the 5 steps that you're going to take are the 2 places where you go right. So we're choosing 2 places, 2 points out of the 5 that we're going to make, that's where we go right. And so the number of ways to do this is exactly 5 choose 2, choosing 2 things from 5, which is 5 times 4 divided by 2, which is 10. Okay, very nice. And this works in general. So if we're going to any old point P, which involves going at some point R steps to the right and U steps up, then the total distance travelled will be R plus U. Let's call that N. And the number of ways to do it is you just choose which of the places along the route will be where you turn right, where you go a step to the right. So you're choosing R things out of a total of N. So it's N choose R. Nice. So why have I told you this? Because there's a different way of working this out. And it's this. To get to that point P, whatever route you take, you'll either, the kind of penultimate place you stop, will either be the place just directly to the left of P, or you'll have come from directly below P. Because you only ever, to get there, you're only ever going right or you're going up. So the last place you have been before P will either be the place directly to the left or the point directly below. So the total number of routes to P will be the total number of routes to that point just to the left, plus the total number of points to that place just below. And that little argument allows you to build up, kind of cumulatively, these numbers. Anything that is a point directly to the right of O, you get no choice about, because there's no up, you just have to go right until you get there. So there's always one route to any of those. If you're going directly up from O, however far, again, you get no choice, because you're never going right, so there's only one route to those. But then those other points, you can add your way to. So this number 2 here, we get it by saying, you've either come from below, there's one way to get there, or you've come from the left, there's one way to get there. And then 1 plus 1 is 2, right? 2 plus 1 is 3. And you can build up and up. And by the time you get to that 10 there, you're adding 4 and 6. So you can build these things up just by adding, which feels nicer than doing all that multiplying and dividing. So you can carry on the grid as far as you like. I'm just going to throw away the furniture there and leave that grid. Now, if I'm going to rotate it now and just show you, because perhaps some of us have seen this triangle before. It's exactly the same thing. I've just rotated it round a bit. And in this triangle on the left now, every number is made by adding the 2 immediately above it. Or if there isn't something on one side, that's an invisible 0. Okay, right. So we can work out these N choose R things by using a triangle like this. We can write it down on a piece of paper and carry it in our pocket if we want to. Now, to cycle back to something we mentioned before, this helps us with multiplying out brackets as well. If you're doing something like 1 plus x all to the power 5, that's in product of all those brackets. What's the coefficient of x squared, say? Well, when you're multiplying that out, how will you get x squared? Well, you're going to have to choose an x from exactly 2 of the brackets. So there are 5 choose 2 ways to do that, which is 10. Okay, so we can, this triangle and these coefficients are exactly the binomial coefficients I alluded to earlier but didn't specify. So they are really, really useful not just for lotteries, but also in working out these other probabilistic calculations we saw before. And this triangle, Pascal wrote a treatise on it, and he wrote about the binomial coefficients, and it's because of that that we now call this triangle Pascal's triangle. I have to say, it was known to Indian, Chinese, Arabic, and Persian mathematicians before Pascal, but this was how I guess we heard about it in the UK from Pascal, so we call it Pascal's triangle. Okay, we now can work out lottery odds. In the UK Lotto, you choose six numbers from 59, and so the number of ways to do that is 59 choose 6, which we can work out with a actually pretty big triangle, right? Or we can use our calculation for binomial coefficients. And we can work it out that the odds of doing this, so there are 45 million-ish. That's 45 million-ish. 59 choose 6 is about 45 million. So the odds of us happening upon the actual correct numbers, the jackpot winning numbers, are 1 in 45 million. Not great odds. Okay, there are other ways you can win some money. So you can match, if you match exactly 3 numbers, you win £30. Yeah, that's all right. So we can do the maths to see what are the odds of that. If you're matching exactly 3 numbers, then 3 of your numbers must be chosen from the 6 winning numbers. So that's 6 choose 3. But then the other numbers, 3 numbers, have to be coming from the 53 not winning numbers. So that's 53 choose 3. And if you multiply those together, you get that there are about 468,000 ways of buying a ticket that matches exactly 3 numbers out of a total of 45 million possible tickets. So if you work that out, it's about a 1 in 96 chance of winning 30 quid, which again, doesn't seem amazing. Okay, but I've got you in here with a promise that you can win the lottery, right? Well, sort of. Okay, so how do you do it? It's easy. It's so easy. What you do is you watch the lottery, you write down the numbers, and then you quickly invent a time machine and go back and buy a winning. No? Okay, I jest. I do remember there was a program a few years ago, a science fiction program, where they decided they were going to do this. Somehow, even though they'd invented a time machine, they couldn't get their grant funding renewed, which, well, it's difficult out there. So what they did, they got the numbers, then they somehow found that they'd only matched 4 numbers. But this is a cute little plot twist, and you might like to investigate which sets of 6 numbers this worked for. When they got to the place to buy their ticket, they looked at the bit of paper upside down. And so, when they found they'd only matched 4 numbers. I don't know if these were the exact sets, but anyway, you can work out all the possibilities. Okay, this isn't my real advice. You don't have to build a time machine. I'm going to present you with 6 ideas to finish off with, 6 ways to maximize your lottery winnings, none of which require you to break the laws of physics. Okay, so the kind of the game is, you've got some budget. Maybe you've got £2 a week, that's how much a lottery ticket costs at the moment. You've got some budget that you can invest in the lottery. What is the way to end the year with the biggest amount of money? Tip number 1, do not play the lottery. Okay, I'm going to have to say this, right? If you don't buy it, if instead you put that money in the bank at the end of the year, you will have £104, and your lottery playing alter ego is likely to have less. The amount of ticket revenue that is given out in prizes is higher than I thought, actually. It's just over 50%. So, of course, that includes the jackpot winnings and everything. Over the very long term, the expected winnings are certainly not 100%. Your lottery playing alter ego will have, on average, at the end of the year, about 50 quid, and you'll have 104 quid. So, this is the way to do it. Of course, if it's fun, that's fine. I think we just have to remember what we're paying for is not the definite likelihood of getting rich. It's that little frisson of excitement of maybe I'll do this, or maybe you like that you're giving some money to good causes or something like this. Never bet more than you can cheerfully lose and be happy and have a smile on your face. Okay, so that's tip number 1. If you must play the lottery, you can play a different lottery. So there are lots of lotteries around the world. Famously, the US Powerball lottery tends to have very big prizes. The reason is the chance of jackpot is 1 in 292 million. that's quite hard to get. So you quite often get rollovers. In 2022, there were 40 draws without a win, and the rollover amount reached $2 billion, which is a lot. The easiest probably one to win is the Polish mini lotto, chance of about 1 in 850,000, because you're drawing only 5 balls and you're drawing them from only the numbers 1 to 42. So you can sort of imagine that that's going to be a lower number of possibilities. At the other extreme, Italy's lotto, 1 in 622 million chance. So again, that's very hard to do. Now, you might think, right, there are in the American lottery 292-ish million possible tickets you could buy. If the winnings reach $2 billion, should I spend $2 per ticket? Should I spend $584 million to get all possible tickets? And I can guarantee I will have a winning ticket in there. Okay, this is no. Of course I'm going to say no. The reason is, what do you think everyone else is doing when there's a Powerball multiple rollover and the prize is $2 billion? Everyone's buying a ticket. Your chances of having to share the jackpot are really quite high. And even, also you have to pay tax on this $2 billion, right? So once you've done that, if you have to share it with even 1 or 2 other people, you are not making money, you're making a loss. So that's a really quite risky. This is why, hedge fund managers are not doing this, right? Because it's a very risky strategy. You're probably going to have to share. There was one instance where a group of people realised, this is in 1992 in the Irish Lotto, which was easier to win, only 1.9 million combinations, tickets were 50p. There was a rollover and the amount reached 1.7 million. And to buy one of each ticket was less than $1 million. And some people tried to do this. They did manage to get a winning ticket. They managed to get an estimated 80% of all possible tickets, which is pretty good, since this was a time you couldn't just buy things online. You had to physically go to shops and buy tickets one at a time from terminals, right? So somehow they managed to get 80% of the tickets over the course of a week. They did have a winning ticket, but they had to share it. Now, they won some subsidiary prizes as well, so they'd never been quite clear about exactly how much they won in the end. It was a group of people, but they may have won a couple of £100,000. They were not millionaires for life, but it has been done. Okay, number 3, join a syndicate. So about a fifth of the jackpots are won by syndicates. If you're in a syndicate, you're kind of spreading your risk a bit. You each put in the price of 1 ticket, say, but then you're actually buying a share of 10 tickets. And so the chances, you're making a little bit higher chance for yourself of having a share of a jackpot, but it's a share. It's a share of a jackpot. So you know that's factored in, right? You're never going to be like the one who wins £10 million, you'll be sharing that. So it's a swings and roundabouts thing. I did wonder, though, if you're buying a bunch of tickets, maybe there's a way to guarantee at least getting a prize. How many tickets do you have to buy in order to guarantee matching 3 numbers, if you're careful about the combinations? Interestingly, I'll just look up the formula. Unsolved problem of mathematics, the lotto design problem. If you can work out this minimum number, then you've got a good maths research career ahead of you. Nobody has got a formula for this in general. There's some little examples. So if you want this number is called L. If you want to be sure of matching 1 number, then if you buy 10 tickets, you can do that because there are 59 numbers, 6 on each ticket. So 10 tickets will mean you can have 1 of each number represented. But of course, you don't get a prize for that. There are some theorems that tell you bounds. So it's known that that you need to buy at least 22 tickets in order to have a hope of matching 2 numbers guaranteed. But the smallest prize is for 3 numbers. And even 22 tickets is already £44. And the prize for 3 numbers is £30. So again, that's not going to help you. There are some specific cases where maybe it can help in unusual rollover type situations, but usually that's not going to be good. Okay, tip 4 of 6. Never buy your ticket on a Monday. This is a UK specific tip, by the way. And the reason is that in the UK, lotto draws are on Wednesdays and Saturdays. So a bit macabre, right? But the chance of winning the jackpot is 1 in 45 million, as we've seen. Unfortunately, anyone's chance of dying in any 24-hour period is higher than 1 in 45 million. So you have a higher chance of dying before you find that you've won the lottery if you buy your ticket too far ahead of time. And even at the extreme of this, I looked up some accident statistics. You have a 1 in 30 million chance, so more likely than winning the jackpot, 1 in 30 million chance of dying from falling over while trying to put your trousers on. So just, okay, be careful out there, right? And if you must gamble, do it at the last minute. Right. So, point 5, don't try and prove a point about randomness. So as we've discussed with coin tossing, any particular set of 6 numbers is just as likely to come up as any other particular set. Whether or not we attach any specific significance to them ourselves as humans. So 1, 2, 3, 4, 5, 6 has a 1 in 45 million chance of coming up. It has exactly the same chance of coming up as this sequence of numbers, or any other specific sequence. They've all got the same chance of coming up. So what we can do, all we can really do, is to try and make sure we don't have to share the jackpot if we win. So, people often choose dates or memorable things, anniversaries, birthdays. So days that can be days of the month, 1 to 31, maybe coming up more often in people's choices, not as draws in the lottery, but what people do, our sort of human way of assigning significance to things. But don't think, well, I know that 1, 2, 3, 4, 5, 6 is just as likely as anything else or unlikely, so I'm going to show that I know this and I'm a logical human being by putting the numbers 1, 2, 3, 4, 5, 6. Because 10,000 people do that every week. So if you do that, then great, you are rational, except you'll be sharing that happiness of being logical with 10,000 other people, and you really do not want to have to share £1 million or whatever the jackpot is 10,000 ways. So don't do that. Final tip. This may be hard to achieve. Be Voltaire. This may be quite similar. So Voltaire and his chum, Charles-Marie de la Condamine, spotted a little loophole in the French lottery. So the French government at that time, they were selling government bonds to raise money, but the interest rate wasn't very attractive. So to sweeten the deal, they had a little lottery attached to it. And you could, if you had one of these bonds, you could, for a little bit extra, so for actually 1,000th of the price of the bond you had, that would entitle you to buy a lottery ticket. So if you had a £10 bond, for 1 extra penny, you could have a lottery ticket. The flaw in the plan was that the prizes you would win in the lottery did not depend on what you paid for your ticket. So Voltaire and La Condamine started buying up thousands of tiny, cheap, there was no minimum price, tiny little bonds, and each one of those tiny bonds gave them an equal chance of everybody else in this lottery. And they did this successfully over several months, and they won a lot of money. They made huge profits, about the equivalent of £6 million-ish in today's money. The government got a bit cross. They actually tried to prosecute them. Took them to court and said, you can't do this. This isn't what we meant. But the court ruled in their favour, in Voltaire and La Condamine's favour. They said, listen, it's not illegal to exploit government stupidity. Right? Your own fault. So the government, they got to keep their winnings. And Voltaire, became a rich man and was perhaps able to devote more time to writing and philosophy. So it's great. Be Voltaire is a good tip in life in general. Okay, so we've reached the end of my little guided tour of the lottery and chance and fate. I'll just mention if you would like to come back here on March the 7th, and if you do, you will hear about the mathematical life of Sir Christopher Wren. But I will stop there. Thank you very much.
Lovely. Thank you very much, Sarah. That was excellent, as always. I shall now have to accuse anyone who's buying a lottery ticket in front of me to stop and be rational, but not too rational about the whole process. I don't know if anybody here wants to ask a question. The only online one we've got is about card counters in Las Vegas.
Uh-huh.
And are they mathematicians extraordinaire, and do they know the probabilities just like that.
So, what is not happening, if the card counters, they are not having sort of prodigious feats of memory and actually memorizing every single card and adding up numbers. Most of the systems that are there assign a value, something like +1 to every low card, say between 2 and 6, and then 0 to 7, 8, and 9, and then -1 to 10 and upwards. And so you've got a running tally in your head, which you're only adding 1 at most or taking away 1 each time. And then there are, triggers of like, if it gets above this amount, that means lots of small cards have been played, so it's favourable. So there's sort of trigger points where you then, okay, I'm going to make a bigger bet. They have to learn these things. They are aware, or at least the people who design the systems are aware of the exact probabilities. You don't have to necessarily know those probabilities yourself to use the system, but what you do have to be, and this is less about actually, when you're playing it, it's less about mathematics and more about nerve, I think, and having a very good memory even under pressure, because you've got to keep this tally in your head. If you're up to 17 and then you get distracted by something, where was I? Oh no, it's all gone wrong, right? So you don't want to be in that position, because as I've said, the actual advantage you get, even playing perfectly, is very, very small and marginal. So yeah, to design the system, you do need to know the probabilities and the mathematics, and so there was a group of PhD students from MIT a few years ago who did manage to do this and made some money on it. But really, it is really, really difficult to do that and stay cool and not get too excitable, so that the people at the casino go, maybe that person, we don't want them playing in the casino. Yeah.
You mentioned earlier that if you tossing a coin, say, and you get a long sequence of heads,
yeah.
And some people think erroneously that a tail must be due. If you're a statistician, you begin to query
yes.
Whether the coin is truly balanced. When did that start coming into mathematics, the statistics, rather than the probability theory?
Yeah, so, I mean, that's a good point. If you did toss a coin and it came up heads 92 times in a row, as actually that happens in the play Rosencrantz and Guildenstern Are Dead by Tom Stoppard. It's a sort of meditation about probability. In that case, they start to suspect something's going on because it's heads 92 times in a row. But in their situation, what's happening is they aren't the masters of their own fate, because unbeknownst to them, they're trapped as minor characters in someone else's play. Hopefully that's not our situation. If that did happen, as you say, a lot, heads 25 times in a row, or lots and lots over a long period of time, you would start to suspect there's something up with this coin. Now, statistics as a subject started to come in, and those kind of analyses over long periods of time, and testing things and hypothesis testing, that sort of thing. Statistics as a subject, I mean, it got its name, I guess, in the 19th century, comes from the German word statistic, but that kind of means state, numbers to do with the state, so measuring things. Initially, it was just measuring things like how many people, what's our population? What's our production of wheat? And then people started to think, we've got all these numbers, we can actually perhaps spot some trends and do some analysis. And so that statistics, it comes from, originally it was just collation of numbers to do with, a country, the state. But then in the 19th century, people like Florence Nightingale, you start to get actual analysis of it. So that statistics as a thing comes a lot later than probability, like 3 centuries later.
Hi there, thanks for the talk. I was thinking about what you said, where we seem to understand ourselves to be really poor. What am I trying to say?
We have a poor intuitive.
Human beings, we're understood to understand probability poorly, and we can't rationalise randomness and things like that. But I'm wondering whether, I suspect it's not an accident that we are like we are, because we're talking about the probability of things which relate to technology, and we didn't evolve with any kind of technology before games, before money, anything like that. And do you think it's because of the status of the natural world that we maybe do expect serial correlation in things and a lot less randomness? So we are how we are actually supposed to be. It's not a fault that we're like.
Okay.
See what I mean?
I see what you mean. So it's sort of actually, yes, our ability to assess risk and things, and randomness is perhaps less prevalent in the natural world because, I think there's something to that. And I suppose my feeling is, you know, the penalty of underestimating risk, if you're just, you know, a hunter-gatherer, is different from the penalty of overestimating risk. If you underestimate risk, go, oh, it's probably not a tiger, I'm fine, then that you know, getting that wrong is unfortunate. Whereas if you say, oh, it might be a tiger for everything, okay, you're a bit panicky, but you're less likely to be eaten by a tiger. So I think we're perhaps something about, you know, the way as we are animals after all, there's less of a penalty for overestimating risk than there is for underestimating it. You know, I'm not a biologist, but that's my suspicion, for sure, yeah.
Thank you. I would like to ask you all to join me in thanking Sarah very much for a really wonderful lecture.